Hello everyone. This is a demo video for E542 Lab 4 Fast Reliable File Transfer. So in this lab, our group has experimented with two UDP-based implementations of reliable transport. In the first experiment, we used a retransmission mechanism that mimics TCP that uh, re we retransmit all packets after uh, a packet drop occurs. So this one, the first experiment is for achieve UDP uh, IP transfer for files. Uh, so why we call it, we will call it TCP-like uh, uh, in the after, because uh, we are based on the UDP IP, and there is no congestion control in the mechanism. So theoretically, the throughput of this mechanism will be higher than TCP, which is true in our experiment. However, uh, this one is still not good because uh, we have so many packets, and each packet uh, need to wait like 200 milliseconds in the environment. So this one, it is uh, it has a slightly higher performance than TCP, but not enough to be called excellent because it's after we test it, it's less than 20 Mbps. So we tried a second mechanism that is selective retransmission, where we send the sender's information to the receiver to create a form, and the receiver will create a lost list that contains which packet needs to be retransmit. So so yeah, it turns out uh, the second mechanism is better, but the workload for the second mechanism for the selective retransmission is uh, kind of big because uh, there are some bugs in our program, such as the sender sends uh, packets faster than the receiver receives the packets. So it can behave well in transmitting small uh, files, but uh, we made some problem in like transfer in 1 GB file because when our packets the sender's packets send too fast, the receiver cannot receive the packets for some reasons. So this is our network topology, which is based on the former labs. So in experiment one, which we call it TCP-like, uh, we call it TL. Uh, in the following. So we test all three cases. The first case is bandwidth 100 Mbps per second, 10 ms delay, and 1% packet drop, while the second case is 200 ms delay and with higher 20% packet drop. In the third case, no packet drop, but the bandwidth is uh, set set uh, to a lower level. So we test these three cases in both MTU of 1500 and 9001. So this is the mechanism for our TL. So the server creates a socket and keep listening for downloading requests from client. While we open client, we are asked to type in the file name we want to download from the server. So when the client send a request to the server begin to send file, and for each packet, the client will send acknowledgement. So, well, if a packet is dropped and the next packet goes in, there will be a mismatch in client packet ID. So the client will send a retransmit request, and the server will transmit the lost packet again, and send all packets after the dropped packet. So this is our results for 6 cases. So let me show you the result. We tested out that uh, it is very like TCP, while with MTU 1500, it's 2 Mbps. It's very low, but it can work somehow better in MTU of 9001, but still in a high latency, and this is 20, sorry, this is 20 loss rate environment. It cannot behave well because too many acknowledgements need to be confirmed in that case. So the file transfer is not that good. But in some better cases with lower latency and lower loss rate, the throughput is approaching like 20 Mbps, but it is not able to exceed 20 Mbps on AWS. So let me show you one case that with bandwidth 100 Mbps, 10 ms delay, and 1% packet drop, and with MTU 9001. So I'm gonna show my code first. So this is the code for client. For MTU, we change this buffer size. For MTU 9001, we use 8192, and for MTU 1500, we use like 1024. This is because if we set the buffer size too large, it will exceed the buffer size, and the program will it cannot transfer file if if the buffer is exceeded. So for both cases, we construct packeting for, and this is for received packets from server. So for client, it is kind of simple. It it needs to know the server IP, to know its address, and then the client create a socket and input the file name to the buffer. So yeah, after that it will send the file name to the server, and it will open a file and prepare to write. So when the server's file comes in, client, it will continue to write in that file. So we can see here. But in such a network environment, it will divide it to two cases. The first one is normal case that no packet dropped. So if no packet dropped, that means the packet ID will equal to uh, the packet ID that server comes in. So if it is successful, we send a packet confirmation back. We set a acknowledgement back to say, okay, we we received this packet, and we write to the file. And the second case is if it is a retransmit packet, we need to set the packet ID to the lost packet and send back to server to tell the server to reset the ID to the lost packet. Yeah, and after that we just close the socket and close the file, and we get a whole file. So for server, it is a little bit complicated than the client. So yeah, for server, this is the same structure. So we need two IDs, the send ID and the receive ID in server. And at the beginning of the program, we need to create UDP socket and bind it. And this socket keeps listening for upcoming requests. So if a request comes in, it will copy that name from the buffer and to find out if the file exists. So if it's not exists, it will say that file is not found. But if if found, it will start the transmission. So this length is for calculating the bytes, that how many bits we send out. So yeah, there are also two cases in server. If no packet drop, the server just sends. and receive the acknowledgement from the client. But if a retransmission request occurs, it the receive ID is is set to the packet the lost packet ID. So you can see this the idea of this program is simple, but uh, we use acknowledgements on UDP to send the to make file transfer with no loss. However, uh, this mechanism requires too many acknowledgements, and it is not uh, it doesn't behave that well in high latency environments because for example, if every packet need to wait for like 200 milliseconds, um, the throughput in the end is very low. So that's why I want to show you uh, this case, because in in this case it takes like about 1 minute, 1 to 1.5 minutes to transfer a day, uh, uh, a 1G file. However, um, however, in other cases, uh, the transferring time is too long, and it is not suitable to show you in this demo video because it needs to transfer like 6 to 7 minutes. So yeah, uh, after we transfer all bits in the file, we just closed it and calculate the time. And also, we need to calculate the throughput and output it. So this is the code. And next I'm gonna show you the yeah, the experiment. So first we set egress rate limiting on both client and server. And then we set egress rate limiting on BIOS. And then we add uh, latency latency and drop rate on VuiOS. Yeah. And we need to move the test file on client. Yeah. And and we need to copy the C file onto the client and server. We compile client TL, and we run server. Yeah, and the socket created and keep listening, and then we run client. So there is a tested file called data.bin. Uh, this is a binary tested file that is randomly caused and its size is 1 GB. So, so we want to download it. And the transmission starts. We can check it here. See if it's, yeah, it's query. So let's wait like 1 minute and to see the result. Yeah, and we can see in this test, file transfer successful. It takes like 90 seconds for 1 Gbps, and the throughput is about 12 Mbps. So we say it performs better than TCP, but it's not that good for UDP transferring. Yeah, and we can see the client here. Now we have a data bin. Can and now we do MD5. They should create a MD5 file for check the data bin. Yeah, and now it has a data bin MD5. So we copy it to client. And to check it, we use MD5. So yeah, and it shows data bin okay, which means we transfer data bin with no loss. So as you see, the throughput between for this TCP-like mechanism is around 10 to 20 Mbps, which is not good enough. So we also tested experiment 2 with several tests. Yeah, and here is some critical thinking from the lab report. You can take a look on report. So yeah, thank you for watching.